All right, recording is rolling. It is Tuesday, September 2nd. Welcome back from Labor Day weekend. So, back on Friday, you guys took a quiz. Here's my top scientist for your very first quiz. So, awesome job. You made the list. Some of you guys weren't here, so you're doing a makeup today. Right. So, you got makeup quizzes for you didn't take that. Linear motion puzzles. You guys remember last week I gave you guys those linear motion puzzles? Oh, it was a page, double-sided, somewhere from your butt, somewhere on some date. So I'm going to start grading those tonight. I have a starter question here. Actually, I think one of the questions we gave you guys to do was pretty similar to this. If you go ball straight up, like how high does it go? So we'll look at that. Oh, no, we do have announcements.
Good morning, Home Nation. Hope everyone had a
All right, we're back. So in the announcements, they mentioned Science National Honor Society. Now, I did post that link back on Friday, so it's on your Google Classroom. I think there was like a QR code going around, but that expired, so they changed it, and this one should work. Right. Oh, while we're here, I did post this over the weekend also. You guys see it says projectile motion puzzles and labs. So this is but by AP's book, this is still part of kinematic motion. It involves the same three kinematic equations that we're going to use today and we've been using the last few days. It's just in two dimensions, right? Because that's what projectiles are, right? You throw something in the air at an angle, right? It goes like up and down, but it goes across the field left to right also, right? Kind of thing. So I do have these printed out. If I don't hand these to you today, then possibly tomorrow. So about midweek, I'm going to start getting you guys going on projectiles. Right. So that's coming up pretty soon. So look for that. I get that out of the way. Let's see, we're over here. Okay, yeah. So we're gonna look at this question. Pick this apart. All right. We'll go through and posters hanging around my ceiling. Some of these gone over explicitly, some not so much. So here I'll go over this to make sure those are all checked off. All right. Now here's where my classes are going to split a bit because I do have an honors class. I'm going to do a Kahoot with them. So I think what I'll do is I will upload this also to Google Classroom. So it's like a conceptual type questions, like how does linear motion work conceptually? There's like 20 questions. They're pretty solid questions. Okay. Trouble is, I only got so much class time. So with you guys, instead I want to do this. You guys see at the bottom says car versus truck free response question. Okay, so I've got an old free response question here. It involves a car versus a truck. I want to get you guys going on that today. We're going to see exactly how the time paces out. Okay. Also, since you guys are AP, there's an AP classroom for Unit 1, which is, again, kinematic motion, which is both linear motion, which we covered a bit of, and also projectiles, which we need to start with the guys about midweek here. Okay, so there's a few, I was going through, make sure that we'll cover all the content. There's a few things I want to mention to you guys, so in time, maybe after these posters, I'll start looking at these. All right, so that's the agenda. We'll come back to this. So one thing at a time here. Any questions so far about anything we're doing? All right, so let's look at this question right here. Let me put the rest of this off. Yeah.
This paper
Or
any additional.
yeah, as long as you don't really work on it. Yeah, do that.
Oh,
Yeah.
all right, but I didn't work on a separate paper, but just.
Oh, so you're not, but
I didn't work for this.
yeah, you can stick with that. Okay. All right, so I throw ball straight up at some velocity. Now, I threw a specific velocity here, 30 meters per second, right? But I'll also have you guys solve this in terms of variables. So you could make this any velocity, and then you can answer this question, like how high does the ball go? Okay. And follow-up question, how much time does it take? Okay. Okay, so who has this figured out by now? Who knows the maximum height of this ball? Maximum height of this ball. Anybody know? Okay. All right, well, if not, how about this? What formula do you think could answer a question like that? If you know throwing speed and you want to figure out how high it goes, what do you think? Okay, so here a nomination for the first one. Here, let's start down the first one. Just see what happens. We'll play around with it. Okay? Sometimes it works, sometimes not. And if it doesn't, maybe that could be insightful. Just like, okay, I see why it doesn't work if it doesn't work. All right, maybe that could help you figure out what does work. So, got a nomination for this one. All right, well, if the question is maximum height, guys, which variable could represent maximum height? Yeah, something to do with displacement. Okay, so at least that's there to be solved. Okay, so that's we're on good track so far. Okay. All right, so I wanted to call this X max maybe I'm solving for. Okay. I know initial velocity was, I said 30 meters per second. So got that right there. What else could you know? Do you know anything else here? Or could something be? What do you think?
Acceleration.
Acceleration. Yes, yes. Because what would be a good number to put right there?
-10.
Yeah, let's go with that. Like you said, negative 10 meters per second squared, right? Right there. Okay. Now, nowhere on the setup, I did this intentionally, did I explicitly mention that, right? But see, like this ball would have to be in a gravity field, right? Because guys, if there's no gravity, what would the ball do? Yeah, like fly into space, right? So okay, and then it would just like go to the edge of the universe, right? So you need a gravity field, okay? And if you're not given any other gravity field, isn't it good to assume that you're probably on Earth? Yeah, yeah, right. Okay, that's a really common thing in this class to if you have to make that assumption, that's a common assumption. Okay? Another assumption is, of course, we're ignoring air drag. Okay? And then see how if you throw the ball upward at 30 meters per second, gravity would be pulling the other way, wouldn't it? Yeah, yeah. That's why, like Justin said, this we're going to call this negative. Yeah. All right. So, what about this t? Do you know this t? Ooh. So that's two unknowns in one equation. I don't know how high, and I also don't know how much time to get there. So can I solve it with just this equation alone? No. Right. So maybe backtrack. Okay, maybe I'm gonna try something else. What's another one? Oh, third one? Here, nomination for the third one? Let's try third one. See what happens. Okay. So I got final velocity squared equals initial velocity squared plus 2ax. Okay. Um, all right. What's something I can plug in? What do you think? Initial velocity? Yeah. All right. So I know this could be 30 meters per second. Now that's being squared here. All right, what else could I know? Okay, yeah, acceleration, of course. So 2 times, about -10 meters per second squared. So right there. What else?
Final velocity.
Final velocity. Well, it's final velocity.
Is it?
Zero. That's right. 0 meters per second. That was a trick. I want to see if you guys could figure it out. You guys did. Yeah. Tristan and Sam got this. So you're saying here, right? Because not everybody figures this out, but some of you guys figure this out. Okay? That if I'm saying something about maximum height, see, like I'm going from this point A at ground level where I'm throwing the ball straight up to this point B where it maxes out. Right? Right, so point A to point B, I care about my initial condition and my final condition. Well, the ball's thrown straight up. You guys see that it would have 0 instantaneous velocity at the very top, right? Where it's like turning around, right? It's not going up, it's not going down. If you point a radar gun at it, it's going to read 0 meters per second right at the very top, just for one instant. Yeah, that's the other thing you got to figure out. And of course, this x could represent h max right here, couldn't it? Represent like that. Is that true? Right, and then you could solve it from there. Yeah, this will definitely solve it for you. Okay. Now, let me do this too. I'm going to split my paper and then solve it 2 ways, right? In terms of variables, and well, I'll say numbers, or how about values? Numbers, values, plugged in from the get-go. Okay. Right, so if I solve in terms of variables, I've got v final squared equals v initial squared plus, we'll say minus 2gh max, right? Or, okay, whether I consider, do I plug in a negative myself or do I consider it after the fact? Right? There's got to be opposite signs somewhere, right? Solve for this h max, right? Right. And then, well, this would go to 0 either way, 0 meters per second, right? Yeah. If I'm solving for h max, right? And if I plug in the numbers, I got 0 meters per second squared, which equals 30 meters per second being squared plus 2 times -10 meters per second squared h max. Okay. All right, over here, right, in terms of variables, let's see, I can add this term over. So 2g h max, which I'm solving for, equals the throwing velocity squared. And then over here, I got, well, so it looks pretty similar. So 2 times 10, 20, I could add that over. So you got 20. I still have a unit of meters per second squared. Got h max on here. and then 30 squared is 900, and that's meters squared per second squared. Okay, all right. All right, and then last step, well, either way, is to divide down this 2g. Okay? So h max, in terms of variables, will always be the throwing speed squared divided by 2 times the gravity field. Okay? Now, if you get that question on AP, like as a free response question, they would want you to derive this starting from the 3 kinematic equations, right? Like if you memorize this, then that wouldn't hurt, but they probably wouldn't want you to just pull this out of your pocket to say, well, start from the 3 kinematic equations and then derive that. Exactly like we just did on this page anyway. Okay, and then this one over here, say divide H max is 45. Okay, then second squared, cancel one of the meters. Left with meters, yeah, which describes the height. Yeah, so the units also work out. Yeah, 45 meters. Guess that. All right. Gotcha. What about this follow-up question? Whoops, where was it? It was how much time? How much time does it take to reach max height? Now, if you want to know something like time, what do you think is a good one to solve for time? Yeah, here are a few nominations for this one here. Okay. Could you, in principle, use the first one if you wanted to? Yes, but you wrote it as what situation starts with the Q? Quadratic, which is like, yeah. So this one looks a lot easier. Of course, it gives the same answer either way. Okay. But yeah, let's do it once a little easier. So final velocity equals initial velocity plus acceleration times time. Okay. Now, you guys told me this is going to be equal to what?
0.
Yeah, 0 meters per second at the top. This could be your 30 meters per second. And then, well, I could say, okay, yeah, plus negative 10 meters per second squared. And then t, we're solving for t. Okay, good. All right, so split my paper again. Solve this 2 ways. Okay, so in terms of variables, it's just going to go final velocity equals initial velocity. I'll say minus gt. That's all right. Okay. And then with the numbers plugged in, it looks like 0 equals 30. Okay, it's meters per second. That's 10 meters per second squared. T. Okay. Right. So then, see, add the. Oh, actually, this would still go to 0 either way. I'll just let that go to 0. Right. Because it's solve for a maximum condition. Okay. Add the gt over. Get gt equals v naught, or over here, I got 10t. This is meters per second squared equals 30 meters per second. Then divide both sides by 10 or by g. Looks like the time is always going to be the throwing speed divided by the gravity field. Right? Or over here. Seconds. 3 seconds. Yeah. All right. Okay. How about this? This was throwing the ball straight up at 30 meters per second. We said the ball would reach maximum height at 45 meters and would take 3 seconds to get there. Is that right? Okay. What about starting from the top and coming back down to ground level? Do you think the number by symmetry, it would also take 3 seconds to come down and it would also be falling 45 meters? So on? Yeah, guys, what would the initial velocity be at the very top? Yeah, 0. Be 0 at the top. Well, here. So going from ground level to the top, yeah, it starts off really fast and it goes slower, and it goes 0 meters per second at the very top. Okay. But it's only 0 meters per second at the top for like 1 instant, like 1 nanosecond. Okay. It comes back down, it's going faster. Yeah. Guys, here, let me see show of hands. See how many guys are getting this. Does it take more time to go to the top, more time to come back down, or does it take the same time both ways?
Same thing.
You guys say same time? Yeah, same time. Yeah, you can show that by symmetry. Yeah, apply these equations here. And you know where else you've also seen this? I dig through is right here. Okay, you guys remember this one? Drop a ball off a cliff and Earth gravity. After 3 seconds, it picks up to 30 meters per second, and it's fallen 45 meters. See, it's the same thing. It was there the whole time. Is it? All right.
Oh, okay, I got that right.
All right. So you guys good with throwing the ball? Okay. You know, I was also going to ask here. Here, let me flip this paper over. Here's a different phrasing of the question. What if I ask this?
Oh, I got
You throw the ball straight up and it reaches maximum height of 45 meters. Actually, this might be a more practical application of the question. Because maybe you could go by some multi-story building, you just throw the ball as high as you can throw it. You see like what floor it goes up to. Right? Knocks on some could be just guy's window. Like, well, that you kind of figure, okay, well, I can kind of figure out how high the ball went. So now I can figure out how fast I can throw. Okay. But you guys see this is going to be the exact same scenario, right? Right. It's just you solve it a little bit different way. Right. Exactly scenario. All right. If you down. Right, so you guys go throwing the ball up. Throwing the ball. All right, let's look at all these posters here, which some of these you guys will see and some not. So let's do a full check off right here. All right, so we're talking about kinematic motion. Here's our variables and units. So x or delta x could be position or displacement. Okay. Yeah, AP, you guys know this from last week. Tends toward using x for position and delta x for displacement. Usually I just call everything x. Right, how far does it go? L could be length in meters. Okay, C, R, sometimes a radial distance. I guess that'll happen later. Okay. H or Y is usually reserved for like a vertical change, but these are all in meters. Okay. Time's taken along in seconds. We see V, velocity could be meters per second. Same concept as mile per hour. Okay. So sometimes I'll say speed, but speed really I'm just talking about the magnitude, like how fast, but not necessarily direction. Okay. If you see the subscripts, I like V naught. I've just always done it that way. Sometimes you see a V sub I for initial velocity, and then VF could be final velocity. Okay. A is acceleration, and lowercase g is a gravity field, which is also kind of acceleration. Got that too. Okay. You know what? Actually, this would be a good time to talk about one of the things I want to talk about anyway, which is average versus instantaneous velocity. Okay. So, guys, as we've been applying these kinematic formulas, what are these V's? Are these V's instantaneous or average? Yeah, guys, these are instantaneous values. These are only true like at individual moments. Okay, so like V could be just some instantaneous velocity. Okay. If CV not VF, those are initial and final velocities, but those are also instantaneous. Okay. If you see, here, sometimes I'll throw a little vector arrow above that. Right. Okay, that's just that just makes it a vector. It's definitely talking about velocity, but same thing, instantaneous. But if you see a solid bar above it, sometimes you see that notation. That's the same thing as V average. Okay, so V average or V bar, same thing. Okay, that's talking about total. Well, he's talking about average speed or average velocity. It'll say displacement or total distance if you're just talking about average speed over total time. Okay, total displacement over total time. Okay. Right. Which does not show up in any of these kinematic equations. Okay. Okay. And what does this look like on a graph? Okay. Suppose you had a graph that was something. Let's do a velocity versus time. So got units. Right. So velocity versus time. Let's put a story together. Let's say there's a car that's parked. Right. So starting from rest. Okay. Start from rest. At time 0, we'd be going 0 meters per second. Center. Okay. Then the guy steps on the gas pedal. Let's say he accelerates uniformly, like pretty much always gets to stop. Guys, can you draw accelerating uniformly? Can you guys draw that? So velocity versus time, you guys do these come out in straight lines, just like they did on your car and incline lab, which you guys got within reach here. Yeah. Isn't that also true on your car and incline lab? Velocity versus time, straight lines. Right. And then actually this isn't the I'm being silly. Okay. Actually, I want to make a different graph. Here, let's make another one right above it. Let's think of something different. Let's do X versus T. Let's do both of these. Let's get a review.
No one knows.
X versus T. Okay. Now let's put this together for the same story. Okay, so let's have the car start at 0.0. And guys, if he's accelerating uniformly, what's that first leg of the journey look like? Not in terms of velocity, but in terms of position. What does this look like? Yeah, parabola. It would be a parabola with taking off like that. Okay. Which is also the same as your current incline graph. There's your current incline right there. X versus t. Same thing. It's a parabola. Okay, how about after it accelerates for a while, then it goes into cruise control. It just goes constant velocity for a while. Because what does constant velocity look like on a velocity versus time graph? Yeah, just flat line. So like his speedometer is showing like 20 meters per second, 20 meters per second, 20 meters per second. Okay. So what does that look like on position versus time? Is it right here? Yeah, it turns linear for a while, doesn't it? Right. Right. So like constant slope, right? And this actually the slope would be the velocity, wouldn't it? Okay. And then let's say it brakes to a stop. Brakes to a stop. What does that look like on velocity versus time?
Slows right down.
Yeah, goes to 0 meters per second. Just make that linear. This class, right? Or slows down at a constant rate. Right. And inside the car, it would feel like a sort of like a constant force type. Okay. As long as this is straight. Okay. And then what does this look like on position versus time? Parabola?
Okay, yeah. We're about to.
Yeah, parabola. Okay. Now, guys, does he go into reverse? I'm going backwards. I'm going backwards. Does he go backwards? No. Is he still going forwards? Yeah, just slower and slower, isn't it? Slower and slower. That like, bing. There you go. There's slowing to a stop. Okay. So here's the gas pedal speeding up. Here's cruise control. Here's slowing to stop. Let's start your shots with some funny noises. Is that right? All right. Now, any one of these coordinates represents an instantaneous value. So this bottom graph, instantaneous velocities, and this top graph, instantaneous displacements or positions. Okay. All right. But if you ever get a question like, what is the average something from a graph? Like, what is the average velocity from beginning to end or something? Guys, average velocity from beginning to end. What you do is I said average velocity. So I'm going to look at the position versus time graph for average velocity. Go from the beginning to the end and just take the slope. Guys, if I take the slope of this line right here, I'll dash it off just so that's distinguished from everything else I have. Okay. But this one right here, this represents V bar, which is average velocity. Okay. Because you guys know the slope of position versus time tells you velocity, right? Okay. Okay, so what about if I said what's the average acceleration from beginning to end? Acceleration. Could you get that from a velocity versus time graph? And what property of v versus t tells you acceleration? The slope? The slope? Yeah. Yeah. So now if I say from beginning to end, then here's the beginning, here's the end. Okay. And then if I find this, guys, what's the slope of this dashed line from beginning to end? 0. So that the a bar equals 0 meters per second squared from beginning to end. Okay. Now, in some places the acceleration was positive. It was, we're speeding up. Now there was 0 acceleration exactly in the middle. Okay. But then when he was ready to stop, there was negative acceleration. But yeah, from beginning to end, yeah, it's 0. Okay. And you might get a question like, what's the average acceleration from here to here? Okay. And then you can just find the slope from there to there, average acceleration. Or what was the average velocity from there to there? Find average velocity from there to there. Okay, so okay, so there. That's one thing I wanted to touch on today was instantaneous values versus average values. Okay. Yeah, and keep in mind all these equation producers refer to instantaneous values. Okay. All right, so got that. Okay, Card incline lab. I think we put together. Did we put together all these? Oh, okay. The only so on your lab we put together these 6. The only one we did explicitly right was this last one, acceleration versus time. Okay. You guys, get a good look at these 3 on the right. You can see X versus T, V versus T, and A versus T. Okay. You guys notice there's the same 3 graphs that I have for the dropping the ball off the cliff. Okay. Guys, remember here's dropping the ball off the cliff. You guys remember these? Dropping the ball off the cliff. Okay. here's
No, that's down.
extra T, V versus T straight from your lab. You guys see that they look like the same
Oh, no,
shape?
it's down.
in shape? Okay. And then if you throw in acceleration versus time, it'd be somewhat constant I. So you guys get card versus card and incline graphs?
It's hard, guys. I don't think we'll- Don't lose all of this, fellow.
So much here. Okay. Guys, let's do car drives at constant velocity. Let's set up 3 sets of axes right here. See if you guys can get these. Apply some critical thinking. I bet you guys apply some critical thinking. We'll be able to figure these out. So how far has the car gone in meters as a function of time and seconds? How fast in meters per second as a function of time and seconds? And what's the acceleration of the car? Meters per second squared as a function of time and seconds. Okay. It's constant velocity, right? You just cruise control, just going, just going. Let's start with the middle graph, the diversity and branch out. Okay. So what does this one look like right here?
Or a bit of really good graph. Straight line.
Yeah, straight flat line. Yeah. So you look at your speedometer, it's showing like 30 meters per second. You're going 30 meters per second there. You're going 30 meters per second there. 30 meters per second there. Yeah. So it's just whatever the speedometer needle is saying. How about how far you've gone as a function of time? What does this one look like? Yeah, it would be a linear relationship. Yeah. Now, if you start at point 0, which I tend to do,
I was looking at the one,
it's just going to go like that. If you started at any other position, like actually you started 3 miles from some town, then could you just shift the sloping up, give it a y-intercept if it 3 miles or whatever? All right, and then how about acceleration versus time? What's that look like?
Also straight line.
Yeah, at what value? 0. Yeah, down here at 0. If there's no acceleration for constant velocity, acceleration is a rate change of velocity. You guys remember that? Here, I'll spell out the definition of acceleration again. Acceleration is change in velocity over time interval. So, but there is no change in velocity for constant velocity. Right? So yeah, it's just 0 acceleration. All right, you guys get on. Okay, there you go. Oh yeah, and these graphs are related to each other. Okay, you guys remember if you accumulate velocity over some time interval, the area under the curve represents how far the car's gone. So you go like 30 meters per second for 3 seconds, that would be 90 meters, wouldn't it? Okay. And then the rate change of your position, the rate change of your displacement, that's what velocity is. That's like a slope on that graph. Okay, so next here. Okay, so here's a good classic question. Can you feel how fast a car is moving? Can you feel the earth spinning? No, right? Because you don't feel velocities, right? Well, in physics, velocities are always relative to something else, right? Like, so how fast are you going right now? You can say, oh, I'm going 0 meters per second. And that would be true. But relative to the Earth, maybe going like 1,000 miles an hour. Relative to the sun, you're going however fast the Earth's orbiting the sun. Relative to the center of the galaxy, well, the sun's moving around the center of the galaxy. Okay, so velocities are always relative. Okay, what you do feel are accelerations. There's 2 big kind of accelerations we're gonna run into the next few weeks. Okay. Actually, this top one is the only one I want you guys to know for the next couple weeks or so. Okay? It's just rate change of velocity in a linear sense. Okay? So final minus initial velocity divided by some time interval. I think we did that last week, right? Did this one. Okay. And actually, if you rearrange this, you get the second kinematic formula. If you just cross multiply that delta t and then add over the initial velocity, don't you exactly get this one? Which is in your notes. Yes, do that. Okay? Now, this bottom one, this is going to show up a few weeks from now, so this won't be for a while. But this is the steering wheel, isn't it? You're bringing the steering wheel. Okay. Here, I'll give it to you now, but this won't show up for a while. So it turns out, however fast you're going, so this would be a speed, not a velocity, but a speed. If you just square that and divide by this radius of curvature, okay, it's sort of like a sideways, right? Acceleration. Right? You guys ever leave the interstate on an off ramp, right? And it feels like something's pulling you to the side. Okay, this much. Yeah, that's it. You can quantify that in Earth gravities or something. All right, brings us to these 3, right? These 3, right? So we've been making good use of these. Okay. You guys remember rule of thumb? If you can identify 3 of those variables, then in principle it is solvable. It's sometimes a little more like sneaky hidden. Right? Like let's say maximum height. You have to say, okay, well, maximum height for a law, note the top, the final would be 0, so it's solid. Do you think you could suppose you were creeping around the galaxy and just landing on different planets? You know, like, I wonder where's the gravity field on this planet. Do you think you could, in principle, like drop balls off cliffs, like time, how much time it takes, and then maybe sort of figure out gravity field from there?
Yes.
Let's see if you can do that. Okay. Here, we'll just do this one on paper right now. Okay. So say you have a cliff of some height. Cliff of some height. Okay. So a little table. Okay. And maybe either like lower a rope and measure how long were the rope, so you can measure, you can get the height, right?
Compare sizes.
Okay. And you bring a stopwatch and okay, so you drop a ball and you measure how much time does it take for this ball to hit the ground. So you have this T, I'll just call it T. And you want to know what is the gravity field of the planet, so you're solving for that. Okay. How could you do that?
V naught.
V naught. Aha. What is this one?
0.
Yeah, equals 0 meters per second. Okay, as long as you drop the ball. It's not true? Okay. Okay, and then, okay, so we're trying to solve this acceleration. You have a displacement and a time. Right? Which kinematic formula is going to get you there?
We're trying to find these ways.
Yeah, you're trying to solve for acceleration.
X and T. First one.
Yeah, I like the first one. I like the first one. Okay, because guys, the first one's the only one that has both the X and the T in it. Okay. The second one doesn't say anything about the height of the cliff, so you can't really utilize that. Plus, it gives you the crash speed, which there'd be too many unknowns here. You wouldn't have this or this, right? But yeah, the first one. Actually, the first one you can simplify. Because guys, if initial velocity is 0, doesn't this term go away? Yeah. See, that's a common simplification. In fact, if you had to simplify it like that for physics, probably just give you credit there. They say H equals 1/2 GT squared, right? Just like that. Times 2 divided by T squared. Gravity field is 2 times the height of the cliff divided by the time to fall squared. That's it. That's the gravity field of the planet. Okay? And it would be in meters per second squared. Hey, look at that. Units work too. Oh yeah. Physics once again. Oh yeah. College. All right. Oh yeah, college. That's fine. Okay. You guys remember this table? Like if I covered up these, you guys could fill in all these.
Yeah.
With kinematic equations to get you there. Right, this is in your notes. It looks just like the graphs from your card incline lab because it's the same scenario. All right. Next challenge question for you guys is: what if we take this up a little bit? What if you're not going to, because this is dropping the ball, right? Dropping the ball. So initial velocity is 0 and so on. Okay. What if you don't drop the ball? What if you throw the ball? Okay, see, I'm going to throw it one or the other way. These graphs look different. Okay. Let's start with throw the ball upward. But let's keep the same direction definitions. Remember I've been saying assume down is the positive direction. Okay. Now AP could go either way, so be ready to handle that either way. And all that, if you change the definition, the graph just turn upside down. So they look the same shape, they're just upside down. Okay. But let's do it. Let's say if you're at the edge of a cliff, here, maybe I'll draw a picture here. Edge of a cliff. And you take a ball and you throw it straight upward. Goes up some and then starts falling back down the cliff. Okay. I want to know what's the height of the cliff as a function of time, how fast the function of time, and what's the acceleration as a function of time. Okay. And remember, I'm defining down as the positive direction. Okay. So to help you guys out a little bit, is if down is positive, let's call it top of the cliff 0.0. Okay. If down is positive, then which direction did you initially throw the ball? In the negative direction. Huh. So should initial velocity be negative? Yeah? Okay. Go ahead. See if you guys can fill in those three graphs right there. What? Just hear your notes. Yeah. X versus T, V versus T, A versus T. So we're covering up the time axis. Huh? Okay, but you know there's a time axis up here, right? X versus T, V versus T, A versus T. Okay. So it's going to look similar to dropping the ball, but not exactly the same. It's going to be a little different. I wonder what's similar and what's different between dropping the ball versus throwing it.
So little below. Really losing. Is it goes up? Whether it really because that's what she said.
Messed that up already. No. Try it again. What? X versus T, T versus T, A versus T.
Even coding at my son.
Alright, let's start with this middle graph. Velocity versus time. Okay. Now, if you threw the ball, again, in the negative direction you guys just said, then where should my sort of like y-intercept be? So time zero, ball is what? Yeah, there you go. So V naught, the initial velocity would be like a negative value, wouldn't it?
Oh, because that makes sense.
Now, as soon as you release the ball, no, it's moving upward, but is gravity pulling down? And is it in free fall? Is it in free fall? Yes, yeah. Because the definition of free fall in physics means the only force on it is its own weight, so it would be accelerating in the direction of gravity. Okay? At the rate of gravity. Okay. What do you think the rest of that graph looks like? Straight line. Yeah. Yeah. You guys are telling me that right there. Is that what you just drew in your notes? Because that's it. That's it. Wait a minute. What's going on right there?
Yes. It's becoming positive.
Yeah. It's zero velocity at this exact point right here, which means that would correspond to the maximum height, wouldn't it? Wouldn't it?
Curves downwards. I felt.
How about
Feeding you.
keep in mind that so the situation is throw upward,
Neurons are binary.
but defined down as positive direction. Okay. Yeah, this is just for the notes today. Remember, AP might give you exactly this. AP might turn the whole thing upside down and say, actually, let's call it positive. And the whole thing just flips upside down. Okay. All right. How about, let's do acceleration versus time. What did that look like, you think?
Started.
Well, acceleration.
Acceleration's gonna be the same. Oh, acceleration.
Yeah.
It's gonna be the same.
Yeah. Okay, so as soon as you release the ball, is gravity pulling down?
Yeah.
Yeah. And when the ball reaches maximum height, is gravity still pulling down at the same rate? And when the ball is falling down, is gravity pull down at the same rate? And that rate would be about 10 meters per second squared on Earth. You guys draw all that right there?
Yeah, you have that.
Okay. Now the tricky one, I think, is height versus time. X versus T. You can call this H if you wanted to. Height versus time. Here, I'm going to define the top of the cliff as 0.0. So I'll give you guys this point for free. Now, because that doesn't have to be true at all. Because I could define the top of the cliff as like at any point I want, basically. But I'll call the top of the cliff 0.0. And so we're saying relative to the throwing position. Look for that to possibly change somewhere down the line, but just for today. Okay. Now, I know there's something special going on right at this point. Okay, so maybe I'll sort of align my graphs. Okay. I know at this time. What was going on at this time again?
It's pretty.
Yeah, maximum height, right? Maximum height. Okay. And remember, okay, we're calling down positive, which means you threw it in the negative direction, right? You threw it in the negative direction because up is negative.
It says right there, down is positive.
So here, I'm going to walk around the room. I'll see if you drew the rest of this graph right.
Close this graph. And I didn't.
Yeah. Oh, just these vertex.
I did.
Close. There's
You're slightly wrong. You get it all right.
So you guys are close.
Because that's where the ball starts. The ball starts at 0.0, so you start at 0 for that. That's great. Yeah, it's almost that. I think I like it.
Okay. Yeah. Ooh. Okay. Let's see what you guys are really close to. Here, guys. If the ball is at maximum height at this time right here, wouldn't that mean that it's the furthest displacement from where you threw it? Okay. So some guys here, I'm going to draw two options over here. Two options. You guys tell me which one's right. X versus T. Okay. There's some V versus T. Here, this dash line right here, I'm just going to bring it up to here just to kind of shortcut it. Okay. Which one's correct? Is it true like here's the edge of the cliff, and then the ball reaches max height, and then when it reaches zero velocity, it's back at the edge again and it goes? Or does the max height correspond to something like that? Which is it, the one on the left or one on the right?
I think it's the second.
See, show hands. How many guys think it's this one on the left? How many guys think it's this one on the right? Yeah, right there. There's the winner right there. Yes. So, yeah, so 0 instantaneous velocity corresponds to the maximum height position. Okay. And then from there, guys, if this is a what shape again? What shape is this? Parabola? So is there some symmetry? Guys, suppose it took like 3 seconds to reach this point. Does it take another 3 seconds to go back to the top of the cliff? Yeah. And now, see if it took 3 seconds. Oh, I guess that means you threw it at 30 meters per second, isn't it? Like the starter question today? Because if you threw it 30 meters per second straight upwards, okay, and then it goes way up, I guess 45 meters, and then it goes back down. Then when it's crossing the top of the cliff again, which is your elevation from where you threw it, guess how fast it's going, but down? 30 meters per second. It's however fast you threw it, just in the opposite direction. Now it's going down instead of up. You guys see the symmetry right here? See some symmetry?
That's so
great.
Beautiful.
Now, so far, here we're going from the top of the cliff, we're going like up so many meters, come back to the top of the cliff. Okay. And now it's free to fall down the cliff. Now the parabola continues. Okay. See that? Okay. There you go. There. Oh, that's throwing the ball upward. Throwing the ball upward. Okay. How about throwing the ball downward? Throwing the ball downward. What's that going to be looking like?
We're not throwing it. It doesn't go up and over. We're just going.
No. Right. So, look at the difference. Now, again, we're going to keep defining down as the positive direction. And if you throw the ball down, then what happens to this V versus T graph?
The line.
Yeah, just shift the whole thing up. Guys, does the slope change? Does the slope line change? No, just the y-intercept, right? Just shift the whole thing up, right? Is the gravity field exactly the same? Is the acceleration exactly the same? Yeah. So acceleration is exactly the same for both, right? Actually, if all you saw was the acceleration, you would have no idea which direction it's even moving. That's interesting. Okay. The V versus T, yeah, you just shift it up. It looks like that. Okay. Oh, actually, this should look familiar, right?
Right.
And then what about this? Guys, X versus T, is it still a parabola? But this time, the ball never goes above the top of the cliff. It starts at the top of the cliff. So we start at 0, 0.
Interesting.
And it goes straight down, doesn't it? Is this still a parabola?
Yeah. Just a weird.
There you go. Right. Yeah, but the vertex does not show up on this graph right here. The vertex doesn't show up on the parabola. Now, if you did mathematically make a vertex, it would be like somewhere like in the past, sort of like down here. Right. But yeah, there's some slope here that's not 0, and that slope represents, guys, what does the slope represent right here?
What? Sorry, I'm looking.
Speed. Yeah. What speed? The speed that you threw the ball. Yeah, speed you threw the ball. Right? Speed you threw the ball. Okay. Actually, I could say the same thing over here. Because this also has a slope right at the origin point, sort of, right? Speed you threw the ball. Versus, go back to last week. If that is the vertex there, what's the speed right there? Is it 0? Because you dropped the ball. Guys, see all coming together?
Oh, yeah.
Okay. You guys remember this from last week? You guys remember this? Right. Velocity versus time. You get velocities, of course, displacements, area under the curve, and acceleration is the slope there. Yeah, okay. There's more I wanted to do with you guys did. That's okay. Things can pace out. That's all right. That's all right. Okay. Guys, coming up, possibly tomorrow, I want to do this with you guys. Do you guys think if you pair it with a friend and one of let's say your friend drops the roller and you catch it as fast as you can?
Like from
Yeah. Okay. The roller will have fallen some distance. And based on that falling distance, you can calculate your reaction time. Okay. So be thinking about this tonight, because yeah, I want to have you guys just possibly tomorrow. See if I can figure that out. All right. Oh, Bell's about to ready. I was gonna do this with you guys. Guys, car breaks to stop. Can you guys keep car breaks to stop? I think we did this one earlier today anyway, right?
Yeah, we did the.
All right. Okay, you guys have a good Tuesday. See you guys tomorrow.
It was always.